Alright, fifth day of our trig unit. I'm going to talk about a couple new things today, but first we're going to do a little bit of review of what we've done. So first problem is the trig puzzles again. So we know that cotangent is -7/4. Cotangent, I'm going to remember that tangent is opposite over adjacent. Cotangent is the reciprocal of that. So if I draw my little reference triangle, I know cotan is going to go to adjacent over opposite. So my adjacent side is 7, my opposite side is 4, and I need to figure out the value of my hypotenuse. Notice this time it's not a Pythagorean triple. That's okay. 7 squared plus 4 squared equals that hypotenuse squared. 7 squared is 49, plus 4 squared is 16. So my hypotenuse squared is that. Let's figure it out. 9 plus 6 is 15. So I'm going to get 65 here for the hypotenuse squared. And so square root of 65 is going to be the value of the hypotenuse. But can we simplify that? Well, yes, we can. Let's see. I know that 65 is a multiple of 5, and I know that it's 15 more than 50, so I know that 65 is the same as 5 times 13, which means I cannot reduce this any farther than it is. So I have to leave it as the square root of 65, which is ugly, but that's okay. We're okay with ugly in this class. So let's leave it there. And what do we know? We want to say what cosecant is. Well, cosecant is the reciprocal of I'm a liar. Cosecant is the reciprocal of sine. So if sine is opposite of our hypotenuse, cosecant is hypotenuse over opposite. So the hypotenuse is root 65 over the opposite, which is 4. But is it positive and is it negative? Well, we need all students take calculus, and we know that cotangent is negative, which means that tangent is negative. Tangent is the slope, so if you think about the slope, where is it negative? Well, it has to be in one of those two quadrants, so it can't be there and it can't be there. We also know that cosine is positive, so we have to be in this quadrant right here. Cosecant is going to have the same sign as sine, and the sign there is negative, so this has to be negative. So our answer should be negative root 65 over 4. All right, next problem, list the 6 trig values for theta when theta is the negative e to the ln of 17 over log base 3 of 81. Mr. Reed, why are you bringing logs into the mix? What are you doing to us? Well, these should be pretty straightforward logs. We know that e to the power of ln of something will simplify to whatever that something is, because e to the x and ln of x are inverses. So that numerator just simplifies down to negative 17, and the denominator simplifies down to log base 3 of 81. 3 to what power is 81? Well, 3 to the 4th power is 81, so we get a 4 down there. And I actually meant to put a pi right there, so let's pretend I did and say negative 17 pi over 4. Let's figure out where that is and list the 6 trig values. So again, the way I do this is I split the top half into 4, and I split the bottom half into 4 because of that 4 in the denominator. And now I count. I start here. I'm going in the negative direction, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and one more 17 puts me right there. So I know I'm dealing with the pi over 4 angle, which means everything's going to be in terms of root 2's over 2. And I know right here x values are positive and y values are negative. So sine is negative root 2 over 2. Cosine is positive root 2 over 2. Tangent, remember tangent is slope. The slope of this line right here is negative 1. All right, reciprocals. Reciprocals here, well, the reciprocal of negative root 2 over 2. So again, the cosecant is going to be 2 over, let's say negative 2 over root 2. But if you rationalize this, you're going to get negative 2 root 2 over 2, which is just negative 2. No, negative root 2. Sorry, it's getting later and later and later and later and later. Okay, well then the reciprocal of cosine is secant, and in a similar fashion, I'm going to get root 2 again, this time positive. And the reciprocal of tan is cotan, and the reciprocal of negative 1 is also negative 1. So I got my 6 values just like that. Zibbity-doo-dah. So again, this here is just hitting the idea. Tangent is sine over cosine. We know that sine is y on the unit circle, and cosine is x. Well, y over x is a rise over run, which is slope m. That's why in the moment ago I was like, well, tangent is the slope there, which is negative 1. So tangent on the unit circle, think about it with slope. All right. Well, now we're going to talk about something cool here called cofunction identities. So number 1 there says express the 6 trigonometric functions of angle alpha as a ratio of the sides of the right triangles. So what it's saying is that sine of alpha is opposite, which is y, over hypotenuse, which is h. And cosine of alpha is adjacent, which is x, over hypotenuse, which is h. And tangent of alpha is opposite, which is y, over adjacent, which is x. And then the reciprocals will get cosecant of alpha is h over y. Secant of alpha is h over x. And cotan of alpha is x over y. Okay, well the next thing we want to do is we want to do the same thing, but we want to do this with our angle beta, which was up here, so I'm going to write it there for now so we can use that. Well, the sine of beta, that's an alpha, the sine of beta is opposite. The opposite side from beta is x over the hypotenuse. The cosine of beta is the adjacent side, which is y over the hypotenuse. And the tangent of beta is equal to the opposite, which is x, over the adjacent, which is y. And then again, reciprocals, cosecant of beta is h over x, secant of beta is h over y, and cotan of beta is y over x. And notice that in the pink and in the purple we have similar pieces. Sine of beta is equal to the cosine of alpha. Sine of alpha is equal to the cosine of beta. And finally, the tangent, not really finally, but the tangent of beta is equal to the cotangent of alpha, squiggly, and cotangent of beta is equal to the tangent of alpha, another squiggly, more squiggles coming up. Secant of beta goes with cosecant of alpha. And now finally cosecant of beta goes with secant of alpha. Okay, that's a crazy little mental map we made right there. What's the significance? Well, think about this other triangle here. Instead of calling this angle beta, think about the fact that we know there are 180 degrees in a triangle in total. So, if we wanted to rename this top angle up here in terms of alpha, we could call it 90 minus alpha, or equivalently in radians, pi over 2 minus alpha. Okay, what's the significance? Well, the significance is we could rewrite all of these relationships. We could say that sine of alpha equals cosine of pi over 2, which is 90, minus alpha, which was our beta angle. We could say that, how do I want to do this? We can say that the secant of alpha is equal to the cosecant of pi over 2 minus alpha. We could say that the tangent of alpha equals the cotangent of pi over 2 minus alpha. That's what this little map right here just did for us. Now we're just spelling it out. And we could go through and do the same thing with the reciprocals. We can say that secant, no, what do I want to do? We could say that cosine of alpha equals sine of pi over 2 minus alpha. We could say that cosecant of alpha equals the secant of pi over 2 minus alpha. We can say that cotan of alpha equals tan of pi over 2 minus alpha. And you may be looking at this and thinking like, holy crap, that's so much stuff I have to remember. But it's not. It's really cool. All it's saying is that whatever function you have, whatever normal trig function you have, put a co with it, and they are equivalent when you subtract the angle from 90. That's nuts. Just stop and think about that for a minute while my voice catches up to me. How do we use this? Well, look at what we have. We have a cotangent function and a tangent function. And notice we have 57 degrees and we have 33 degrees. Well, think about this. Cotan of 57 is the same as 90 minus 33. And then we have our minus tan of 33. Well, the cofunction identity says that cotan of 90 minus 33 is the same as tan of 33. So we have tan of 33 minus tan of 33. Well, that's the same thing, so it's got to be 0. If you didn't know the cofunction identity, you'd look at cotan of 57 minus tan of 33, and you'd be like, there's no way I can do this. But with the cofunction identities, it ain't no thing. Okay, well, what about this one? This one is a thing. It's a little more involved, but it's still really not. Oh my gosh, that was so funny. I just moved to get more comfortable, and my dog popped her head out of the blanket like she was like a whack-a-mole or something. Well, here we're going to need to use a couple things. We're going to not only need to use a cofunction identity, we're going to need to use what we know about even and oddness. We know that cosine is an even function. So, hi doggy. So, we know that cosine of negative pi over 3 is equivalent to cosine of positive pi over 3. Cosine of positive pi over 3. That's what evenness means. It means you can get rid of that negative. It doesn't matter. It doesn't change it for cosine or for secant. Okay, well, what about this cosecant of pi over 6? Actually, what about this 1 over cosecant of pi over 6? Well, it's getting really complicated here, but think about this. Cosecant is the cosecant goes with sine. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. But we're doing 1 over hypotenuse over opposite. Well, dividing by something is the same as multiplying by its reciprocal. So really, 1 over cosecant is the same as, if we have opposite over hypotenuse, that's sine. So really, we can replace this with just sine of pi over 6, just like that. And you could go through and you could figure these out just, using what you know from the unit circle. We know that cosine of pi over 3 is, well, I'm really tired now. What is cosine of pi over 3? If you don't know, draw a little unit circle pinwheel thingy. Pi over 3 is right there. That's where cosine is 1/2. And what is the sine of pi over 6? Well, sine of pi over 6 is right there. Hey, look, that's also 1/2. But another way to think about it is that pi over 6 is the same as pi over 2, which is our 90, minus pi over 3. Another way of saying that is pi over 2. I don't want to say it the other way because we know that pi over 2 minus pi over 3 get a common denominator, so sixths. So we can get 3 pi over 6 and 2 pi over 6. 3 minus 2 gives me the pi over 6 right there. Regardless of how you choose to look at it, the point remains that sine of pi over 6 is the same as cosine of pi over 2 minus pi over 6, which is cosine of pi over 3. And again, we get cosine of pi over 3 minus cosine of pi over 3 has to be 0. So I give you another value that's just equal to 0. Okay, here's another one. Again, it's not so obvious, but we have 1 over secant. Secant is the reciprocal of cosine. So if you're taking the reciprocal of a reciprocal, you get back to the original. 1 over secant is going to be the same as just cosine. So we have cosine of pi over 6 plus tan of pi over 3 sine of pi over 6. Well, what is tan? Tan is sine, so let's say sine of pi over 3 over cosine. So cosine of pi over 3. Oh, my bad. That video was still playing. I thought I paused it. Apparently I didn't. I was, for some reason, I was tapping my teeth with my finger. I don't know why. But we have that, and we still have times sine of pi over 6. And somehow we need to simplify this. Well, we should try and get all these angles to be the same. So actually, I'm going to go back a step, and what I'm going to do is I'm going to change tangent to cotangent using its cofunction identity. So tangent of pi over 3 will equal cotangent of pi over 2 minus pi over 3. Well, what's pi over 2 minus pi over 3? Well, it is pi over 6. So I get cotan of pi over 6 times sine of pi over 6. And now it's good because everything's in terms of pi over 6. But what is cotan? Well, cotan, if tan is sine over cosine, cotan is cosine over sine. So I have cosine of pi over 6 plus cosine of pi over 6 over sine of pi over 6 times sine of pi over 6. And boom, boom, those cancel. So I have cosine of pi over 6 plus cosine of pi over 6, which is 2 times cosine of pi over 6. And I know that cosine of pi over 6, well, again, draw a little unit circle. Pi over 6 is not there, but it is right there. And the cosine is root 3 over 2. So I have 2 times root 3 over 2. The 2's cancel, and I get root 3. And my dog is clawing at the door, so she needs to go pee. I will be right back. Okay, so those are cofunction identities. You need to think about using those sometimes. A good idea is if you have two different angles in the same problem, and I'm asking you to simplify it algebraically, you should check and see if you have cofunction identities that you can use. Think about this. The whole idea is you're looking for a difference when you subtract from a 90-degree angle, but we're doing it in radians. So think about what you know. If you subtract pi over 3, this angle, from that full pi over 2, what do you get? Well, you get the little squiggle left right there, which is pi over 6. Because we know if this is 60, then this is 30. Sometimes it helps to think about the actual degree measurements. Same way, if you subtract that 30, which is pi over 6, from pi over 2, you get the 60, which is pi over 3. If you subtract pi over 4, you get a pi over 4, halfway right down the middle. Okay, so a couple other identities we need to talk about that are just as good are the Pythagorean identities. So we're going to use a Pythagorean theorem using these little generically labeled triangle. So we're going to get the hypotenuse squared. It's going to equal the opposite side squared plus the adjacent side squared. It's just a fancy version of the Pythag theorem right there. But now think about what we can do. Again, we want to find some way to apply this to a unit circle. So let's make the length of the hypotenuse 1. In order to do that, we need to divide everything by h squared. So we get h squared over h squared is 1 equals opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. Well, if you know your rules of exponents, we can rewrite this as 1 equals opposite over hypotenuse quantity squared plus adjacent over hypotenuse quantity squared. Well, what is O over H? We know that opposite over hypotenuse is sine. So really what we have here is sine of whatever our angle is squared plus adjacent over hypotenuse is cosine of whatever our angle is squared. And typically you will see this written when you square a trig function. It's written like this. It's written as sine squared theta and cosine squared theta. But this lovely little formula is the Pythagorean identity. It's very powerful. You can simplify many things with it. And we're going to look at how to use it in the coming slides. But before we do, we're going to use this formula to come up with two other formulas. And to get those two formulas, it's very quick, it's very painless. All we need to do is divide by either cosine squared or sine squared. So let's divide both sides by sine squared theta, sine squared theta, sine squared theta. What do we have on the left? Well, sine squared theta over sine squared theta is 1 plus, what's cosine squared theta over sine squared theta? Well, what is cosine over sine? We know that tangent is sine over cosine, so cosine over sine has to be cotangent, and it is squared. Well, what is 1 over sine squared theta? Well, that is the reciprocal of sine squared theta, and we know the reciprocal of sine is cosecant, so we get cosecant squared theta. So, from the first Pythagorean identity, we very quickly and painlessly came up with a second Pythagorean identity, which is just as useful as the first. Let's do it again, except this time let's divide everything by cosine squared theta. So divide everything now by cosine. And what do we get? Well, sine over cosine is tangent. So this time we get tangent squared theta. And cosine over cosine, cosine squared over cosine squared gives me 1. So now I have 1 plus tan squared theta equals 1 over cosine. Cosine's reciprocal is secant, so I get secant squared theta. And so now I have two new Pythagorean identities. Get the third one in there as well, just for fun. We get, blah, blah, blah. How do I want to write this? I guess I want to write it like I would normally write it. Sine squared theta plus cosine squared theta equals 1. And you can manipulate these equations. You can rewrite them in any algebraic way you want. Subtract cotan squared from both sides of that pink one to get 1 equals cosecant squared minus cotangent squared. Subtract tan squared from the middle one to get 1 equals secant squared minus tangent squared. And do whatever you want. I don't care how you manipulate it. Sometimes you're going to need to rearrange it. So my advice to you would not be to remember these formulas, not to memorize them. You need to know the Pythagorean one, but that's easy. Cosine squared plus sine squared equals 1. But then the other ones you should just quickly be able to come up with on your own. So we have these. Now let's look at how we can actually use them. And it's going to be similar to what we did with the cofunction identities a moment ago. So look at this mess right here. Golly, what are we going to do? Well, let's use our Pythagorean identities. And I was going to just copy and paste them, but I want to show you how quickly it is to just come up with them. So this is what I would do. I know that sine squared plus cosine squared equals 1, and I have 1 minus cosine squared, so if I subtract cosine squared from both sides, I get 1 minus cosine squared over here, which means that I can replace 1 minus cosine squared of pi over 6 with simply sine squared of pi over 6. And I'm multiplying this by secant of pi over 3. So notice we have a pi over 6 and a pi over 3. We're dealing with cofunction identities now as well. Oh my gosh, Mr. Reed, why are you making it so hard right off the beginning? Well, because you can handle it. So sine squared of pi over 6 times secant of pi over 3, the cofunction identity of that is going to take us to cosecant of pi over 6. And so what is cosecant? Well, cosecant is the reciprocal of sine. So I have sine squared pi over 6 times 1 over sine squared pi over 6. Boom, boom. You get 1. So that ugly mess is simply 1. Crazy. Sorry, sorry folks, I goofed. Did you see what I did? Maybe you did, maybe you didn't, but let's run back through it real quick. My mistake came right there when I squared this. Sine squared of pi over 6, that's cool, it's staying. But here I have cosecant of pi over 6, and I wrote it as if it were cosecant squared. But if I just have cosecant of pi over 6, this needs to be 1 over sine of pi over 6, not sine squared of pi over 6. So that sine of pi over 6 will cross off one of those sine of pi over 6 squareds. So I'm left with the sine of pi over 6, which is the same as the sine of 30, which is 1/2, not 1, 1/2. Okay, we're going to do two more here. Again, I'm simply going to start by writing the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. How can I manipulate this to simplify other stuff? Well, I can recognize that I have 1 minus cosine squared. So again, I can rewrite this as sine squared theta equals 1 minus cosine squared theta right there. And now I can substitute in to get sine squared pi over 4 in the numerator there over that secant squared mess. So let's figure out what that secant squared mess is going to simplify to. So if I take this Pythagorean identity, this lovely dude right over here, and I want secant, secant is the reciprocal of cosine. So I want to divide everything here by cosine squared. So let's divide that by cosine squared and that by cosine squared. What do we get? Cos over cos gives me 1 on the left, plus sine over cosine is tan. So I get my tan squared theta there, equals 1 over cosine is indeed secant squared. And I want secant squared minus 1, so let's subtract 1 here, move this 1 over. What do we get? Well, secant squared theta minus 1 has to then equal tan squared theta. So this is going to be the same as tan squared pi over 4. But what is tan? Well, tan, so I'm going to rewrite sine squared pi over 4 over tan is sine squared pi over 4 over cosine squared pi over 4. What do we always say when we're dealing with fractions and fractions? Well, we say that dividing by a number is the same as multiplying by that number's reciprocal. And so instead of dividing by sine squared over cosine squared, I will multiply by cosine squared over sine squared. So I'm going to get cosine squared of pi over 4 over sine squared pi over 4. Boom, boom. Those will cancel out. And I'm left with cosine squared pi over 4, which is equivalent to cosine of pi over 4 squared. Cosine of pi over 4 is root 2 over 2. I need to square that, so I get 2 over 4, which, again, is 1/2. I like giving you the same answers for some reason. I don't know. Is this the only way to simplify this? Absolutely not. Absolutely not. There are other ways, but that's the way that jumped out to me immediately. So that's the basics of cofunction identities and Pythagorean identities. They're very useful because we can simplify seemingly complicated things down into simpler problems. The cofunction identities come from that right triangle, simply looking at the two angles, and the Pythagorean identity comes from just simply using the Pythagorean theorem on a right triangle. Pretty cool. One other thing to think about is that the equation of a circle, you may remember from last year, is x squared plus y squared equals r squared. So in the unit circle, we get the equation x squared plus y squared equals 1, because the radius is 1. Well, what do we know is the same as x? We know x is cosine of theta. We know y is sine of theta. So we can substitute that in to get cosine squared theta plus sine squared theta equals 1. Another way to think about the Pythagorean identity.